In this video, our fourth in the series of 4 videos on flammable solids, we're going to talk about flammable nonmetals. Now, nonmetals are capable of reacting with oxygen, just like metals do. And when they do, they form these nonmetallic oxides. So here's a classic example of just that. And with a little bit of balancing here, we have a balanced chemical equation that tells us the reaction that exists between phosphorus and oxygen to create diphosphorus pentoxide. Now, when these substances react with water, they can produce acids, and these are actually the precursors to a lot of different acids. And the reaction there is pretty simple as well. 3 of those and 2 of those, and you've got yourself phosphoric acid. Now, these are common reactions that can occur, and we see these reactions a lot. So not only are the elements themselves flammable, but the products that they form actually produce corrosive materials, which make the products of the reaction dangerous in and of themselves. So let's take a look at some of them individually here. So if I look at phosphorus, phosphorus comes in a lot of different forms. Each one of those forms is something we call an allotrope. An allotrope is basically a different structure design that exists within an elemental sample, and the different structures give the elements different kinds of properties. We most commonly think of allotropes when we think of the difference between carbon in the form of diamond and carbon in the form of graphite. Both of them are carbon at their very core. They all have all carbon atoms. The difference is in the structure. The structure of the carbon diamond is a series of tightly networked carbon atoms that all are bonded to 4 other carbons, forming this tetrahedral network that's very strong and very rigid. Whereas in graphite, you have carbon forming bonds with 3 other carbons and forming these 6-membered rings as a result. And the 6-membered rings are more flexible. They're a little bit more movable, and so as a result, they tend to glide over each other instead of breaking on, or forming this rigid structure. Well, phosphorus has these as well, and the most common allotropes that we see with phosphorus are white phosphorus, which is shown here on the left, and red phosphorus, which is shown here on the right. Now, white phosphorus is, in general, a white, waxy kind of solid, and it appears yellow mainly because of a transformation that takes place. White phosphorus is unstable, and when it reacts in the air, it will gradually change. Oh, excuse me. When it reacts with light, it'll gradually change to form the red phosphorus. And so, as a result, white phosphorus always has a little bit of a yellow tint to it because there's always just a little bit of transformation that's taking place inside of it. Now, white phosphorus is pyrophoric. When it comes into contact with the air, it immediately ignites in a brilliant kind of flame. White phosphorus is also toxic and can cause some severe liver damage if it is ingested. White phosphorus is the most lethal and the most unstable form of phosphorus. But the good thing about white phosphorus, if you can think of it this way, is that it does not dissolve in water. And so, how do we keep it from exerting all of these properties? Well, we store it underwater. And if you store it underwater, it loses its pyrophoria, at least as long as it's under the water. And it's obviously not going to be toxic unless someone takes it out of the water and tries to ingest it. Now, when it is transported, it is usually transported in the liquid phase. White phosphorus, and as most nonmetals, is pretty easy to melt. So with some slight heating, we can liquefy it and make it easier to transport. Red phosphorus, on the other hand, dark red powder. In fact, red phosphorus is the phosphorus that we associate with matches and match heads. That dark red color that comes on those match heads comes from the phosphorus that is on those matches. Now, red phosphorus is actually an intermediate phase. It's what exists between white phosphorus and another allotrope known as violet or purple phosphorus. Now, red phosphorus is not nearly as reactive as white phosphorus is. It's not pyrophoric. It will not ignite at all at temperatures below 260 degrees Celsius. But when friction is applied, it can burn, and that's why it's used in things like matches and flares and gun caps, as well as some other kinds of pharmaceutical applications. Sulfur, on the other hand, sulfur exists in a number of different allotropes as well. The most common is this bulky crystalline structure that we're most familiar with. And that bulky crystalline structure is an 8-membered ring where each one of these atoms in this ring is a sulfur atom. And so this is commonly referred to as crown sulfur. Because of this configuration, the sulfur does seem to have a crown kind of shape to its molecule. Sulfur on its own, relatively odorless, does have a faint odor, bright yellow crystals that can take on a number of different kind of shape forms depending upon the circumstances. Where do we find it? Most commonly, we find sulfur in hot springs, in areas where there is volcanic activity. And so most commonly we find it in places that are on the Pacific Ring of Fire. So we're talking about the west coast of the United States and Canada. We're talking about the eastern coasts of China, Japan, and some of the Russia, some of the other countries in that upper eastern zone where there's a lot of volcanic and a lot of earthquake activity. Sulfur very easily melts 100 degrees, sublimes quite easily as well, can burn. When it does burn and from that vapor state, it gives off sulfur dioxide, which is just a really choking kind of smell. If you get it in any kind of concentration, it has a tendency to kind of take your breath away. In lower concentrations, we associate its odor with kind of like a burnt hair smell. But otherwise, if you get a good whiff of it, it actually can kind of choke you to a degree. It can make you start coughing. And part of that is its toxicity, and part of it is just that's kind of its nature. Sulfur is a component in black powder, which is a mixture of saltpeter, potassium nitrate, charcoal, which is why it's black, and sulfur. Sulfur on its own is a non-toxic material, it is insoluble in water, but its reactivity is what makes it show up on our watch lists as something to be aware of. Now, the last class of non-metallic substances that we're going to look at are these water-reactive compounds that produce acetic acid. Now, acetic acid you know better as vinegar. Vinegar that you buy at the store is a 5% solution of acetic acid in water. And so, because of that tendency, because of that reactivity, we do know that things that create acetic acid are obviously going to create corrosives, which is a problem unto themselves. And usually the substances that we're talking about here that react with water are also going to have some other inherent dangers as well. So what do we know about acetic acid? Well, we know it's got a really pungent odor. If you think about what does vinegar smell like, it's a pungent, acrid, kind of irritating odor. It's very hard to get rid of. When we inhale that vapor, it can be suffocating, especially if it's at a high concentration. If you put your nose up to a big cup of vinegar and take a big old whiff like that, it's going to have an effect on you. You're going to cough and you're going to choke just for a second because it's quite irritating and a little bit suffocating. If you get exposed to it in your eyes or nose, it can be very irritating as well. Now, here are some of the things that help to create it. For example, acetic anhydride. Acetic anhydride is a colorless fuming liquid. We use it for a lot of different industrial purposes. Probably the most common is the production of aspirin, but also cellulosic materials like cellulose acetate and other related products. Um, this stuff, when it reacts with water, will produce acetic acid, and we'll get all the effects associated with the acetic acid that way. Acetyl chloride, also a colorless fuming liquid. Acetyl chloride is used in a lot of different industries as an organic substance. And when it reacts with water, we get a really violent reaction that takes place. We get acetic acid formed. We also get hydrochloric acid vapor, and so this stuff is really dangerous if it comes into contact with water, because not only do you get the acetic acid, you get vaporized hydrochloric acid, and as we've talked about in previous discussions, hydrochloric acid is a strong acid. It's highly corrosive, and in the vapor phase, oh, it is even much more reactive and a lot more dangerous because of how easily it can go from one place to another in that vapor phase as opposed to the liquid. Now, in either case, um, putting out fires or other kinds of issues with them, we would recommend carbon dioxide, but probably preferably dry chemical. So either your BC or your ABC fire extinguishers would be useful in these cases. Because most of the reactions that they are producing, in fact, involve the production of vapors, using fully encapsulated protective clothing and self-contained breathing apparatuses are recommended, if not required. And because of the reactivities with water, you cannot use water as a fire extinguisher in these kinds of fires. All it's going to do is to promote the problem by making more acetic acid, making more corrosive materials, in some cases making more hydrochloric acid, which is even more corrosive, and causing problems in that way as well. So this concludes for us our look at the air reactive and water reactive substances. In our next set of videos, we will look at some toxic substances in Chapter 10. Have a good day.